Test, 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 test. Okay, can everyone hear me? Yeah. Alrighty. Just making sure everyone's here for the Steins Gate panel, like it says right here, right? Yeah. Okay. Let me just introduce myself. I'm Anthony, also known as Blickwinkel, the translator, or one of them, for the Steins Gate visual novel. I'd just like to make an announcement before we start. Steins Gate 0 will come out in English on PlayStation Vita and PlayStation 4, November 25th in Europe and November 29th in the United States.
This year, right?
This year, yes.
Any news on PC release for English?
I cannot say anything about that. But there is a Japanese PC release, so you never know. Okay, so let's start off here with the science of Steins Gate. Okay, so instead of just going over every little scientific inconsistency, we'd be here all night if I did. I chose two major topics, one of which is everyone pretty much knows that's blatantly wrong. Another one people think is blatantly wrong, but is actually pretty plausible. So first off, we have data in event horizon. Can a black hole really compress 3.24 terabytes of data into 36 bytes? And just spoilers, heads up, no. And the second topic is fractal epigenetics. You are what your mom eats. Oops. Okay, so for the black hole compression, here's what Steins Gate says. Yeah, let's just hack into CERN, borrow the LHC, and transmit some data into a black hole that the LHC generates. Because everyone knows that the LHC makes black holes, right? Yeah. And then you could use the black hole to compress 3.24 terabytes of data into just 36 bytes. Side note, if you see any handwriting in the original Steins Gate game in English, that's my handwriting. Oops. So the two main things that are wrong with the black hole compression, the logical holes in the black hole, so to speak, are that it conflates data and medium, and then also just doesn't really understand how computer compression works. So the way data is transmitted through a medium, you're not transmitting the actual data. You're transmitting a representation of that data, because data isn't physical, so it has to be stored in a medium. The simplest way is binary data, a 0 or a 1, on or off, 5 volt or 0 volts, hot and cold, yes and no, in and out, all that stuff. So wireless data, you represent the zeros and ones as waveforms, and the three main ways of doing that, amplitude, there's amplitude, you can either code it by amplitude and say zero has a short wave, short amplitude, and 1 has a tall one. Or you can do it by frequency, where low frequency would mean 0 and high frequency would mean 1. Or you can do phase shift, where the position in the wave, if the wave is like at the top at 1 second, that would be 0. Or if it's like at the bottom at each second, then that would be the other one that I said. So what's wrong about conflating data with the medium is that no matter how much you compress the medium, you're not actually compressing the data in it. So we have here a really mini Bible, and then we have a very large print Bible. Assuming that it uses the same translation of the Bible, then both of these Bibles contain the same data, regardless if one is big and one is small. It's like a pound of feathers and a pound of steel, there's still a pound. So as a side note, the Bible is 4.13 megabytes in size, and Steins Gate is 1.78 megabytes. So basically, if you call Steins Gate the Old Testament and Steins Gate 0 the New Testament, Steins Gate is about a Bible in size. So before we get into how compression works, let's just see exactly how small is 36 bytes. And I put up there just a few different representations of 36 bytes. 36 ASCII characters. So this raw text is 36 bytes long total. Or 18 Japanese or Chinese characters, because those are 2 bytes each. Kono texto no nagasa wa 36 baito desu. Or a 288 monochrome bitmap image, because each pixel is 1 bit. And this isn't including the header, because if we include the header, you wouldn't be able to fit any image data on it, because bitmap headers are 54 bytes. So you couldn't even send like, hey, this is an image, much less that image. And then if you wanted true color, which is 3 bytes per pixel, 1 byte for how red it is, 1 byte for how blue it is, 1 byte for how green it is, then you're only going to get 12 pixels. It's really hard to use a touchscreen with gloves. So let's go on to data compression. It's like a short joke to kind of drive in what data compression is. So if you set your Wi-Fi password to 244666688888888, you could tell people that your Wi-Fi password is 12345678. So, what that shows is that data can be redundant. And you can use the redundancy to compress the data to say the same thing in fewer letters or numbers. So the original number is 16 digits, but the number of digits in 1, 2, 3, 4, 5, 6 is just 8. But that's not entirely. This sort of compression isn't very. It's not very useful in the real world. So let's go over to actually used algorithms, just a little basically. So we have Lz77. They made a bunch of different ones that are kind of the same. Lz77 is kind of the most basic. The LZ stands for Lz77 is 1977. And we also have Huffman Coding. So the way Lz77 compression works is when you keep going through the text, and if you see something that looks familiar, you just replace that with the number of letters that you need. Can you see? No, I'm just, okay, yeah. So you just replace a repeated string with how many letters you need to go back, and then the second number says how many letters you need to copy. So here we have the sample sentence, comparing computer compression session, and that has a bunch of repeated syllables that you can just replace. So we have comparing, and then we reach comp again, so we just say, oh, go back 10 letters, and then copy the next 4. So then instead of having comp again, you just have that 2-digit number, and then same with the second comp, but there's a space, so you can copy 5 characters. And then again with the Eschens. So the original sentence we have is about 40 bytes, and compressed you get about 29 bytes. So that's pretty good compression right there. Huffman coding is a little bit more difficult. I'm not going to go over how you make that tree, but basically, you know how I said that ASCII characters, it's 1 byte per character. 1 byte is 8 bits. You can save a little bit by using your own kind of code. So you take the most frequently used letters that you use, and you give them a shorter code than the letters that you use least frequently. So here C, E, O, and S are 3 or 5 times used in that sentence, whereas the T, U, G, and A are only used once. So C has a code of 000, but A has a code of 01010. And I'm not going to read out that string of 1 and 0s, but the original size is 40 bytes, and compressed we get 18 bytes, or 140 bits. So the deflate algorithm uses a combination of Lz77 and Huffman Coding. And you should be familiar with the deflate algorithm if you've ever used .zips or .pngs, because those use that sort of algorithm. So let's get to the meat of the question. Can you compress a 3.24 terabyte file into 36 bytes? And the answer is yes, you can. The caveat is that not all of them can. So say you have a 3.24 terabyte file that's just the letter A repeated 3.24 trillion times. If you use Lz77, you can just compress it into something that says A, and then go back one letter and just repeat that letter 3.24 trillion times. So why can't you compress any 3.24 terabyte file into 36 bytes? There's something called the Pigeonhole Principle. Basically, if you have more pigeons than you have pigeonholes, and you put all of your pigeons into pigeonholes, then at least one pigeonhole will have more than one pigeon inside of it. So here we have 3 pigeons and 2 pigeonholes. So you can't compress 3 pigeons into 2 holes and expect to have a 1-to-1 pigeon to hole ratio. So basically, we have in a 3.24 terabyte file, we have 2 to the 8 times 3.24 trillion pigeons, and the number of holes we have is only 2 to the 36 times 8. I bet you can tell which one is smaller. So there's a bunch of dumb little math. Basically, there's an essentially infinite number of possible memory sets that you can have, and only a finite number of 36-byte files that you could compress those into. Then if you want something simpler, speaking statistically, the average adult English-speaking speaker has a vocabulary of 25,000 words. So I went and looked up the 25,000 most used English words and put them into a file. That file turned out to be 226 kilobytes raw. And when I compressed it, it was 100 kilobytes. And so 100 kilobytes is about 3,000 times as much as Steins Gate's 36 bytes. So if you sent a full human memory back into the past, just 36 bits, they wouldn't even be able to remember all of their words. So just in conclusion for that, real compression, you can usually get a file down to 50 to 80% of its original size. And with black hole compression, you can get it down to 0.0000 lots of zeros, 1% of the original size. So now onto the fractal epigenetics, where we get into Luca's genes. I mean the genetics. So what Steins Gate says, and this is why a lot of people find an issue with this particular thing, is that Luca is conceived, and then during pregnancy is when they send the message back to Luca's mom via pager that, oh, you should eat lots of green vegetables so that you have a healthy child. And it's like, but it's psych. It should make your child grow into a woman instead of a man. So a lot of people take issue to this because they say, like, high school genetics says that that at conception is when your genetics are decided, and there's the you get either an X chromosome from your father or a Y chromosome from your father, and that is what determines your sex for life. So people say, oh, XY means male, XX means female, and nothing during pregnancy will change that, right? Well, I wouldn't be talking about this if I had anything more to say. So let's go on to methylation and how exactly something during pregnancy can change the expression of genetics. So Um, just going over some more basic high school genetics. Your stem cell, so you have stem cells and they differentiate into all of your body cells. Each of your body cells contains your entire genome, right? But only your stomach knows to make stomach acid, right? It'd be kind of painful if every cell in your body produced stomach acid. So how do your cells know? How do your cells know not to produce? How do your cells know what to produce and what not to produce? And the answer to that is in part methylation. Basically, methylation takes your DNA and just shuts off certain genes so that they don't get expressed. So how does methylation work in the womb? Well, during pregnancy, the fetus is very susceptible to the conditions of the mother. You see things like children inheriting AIDS or drug addictions because of the mother. So one example of methylation affecting the expression of genes is the agouti gene in mice. Agouti causes obesity and a yellow fur in the mouse. These two mice are the same age, and they both have the agouti gene. They both have the agouti gene, and yet only one of them is yellow and fat. How did that happen? Their mothers were fed different diets during pregnancy. The yellow and fat mouse had its mother was just fed a regular diet, and the normaler looking mouse, his mother was fed a diet supplemented with choline, folic acid, betaine, and vitamin B12. And that somehow encouraged methylation to the point where the agouti gene was mistakenly methylated and did not express itself in that mouse. This is called epigenetics, which is the reason why I titled the section Fractal Epigenetics. So, what contains choline, folic acid, betaine, and not exactly vitamin B12? Leafy vegetables. I say not exactly vitamin B12 because vitamin B12 is actually found in bacteria, and this bacteria in many countries is found on leafy vegetables, but in other countries that sterilize their produce, you might see a little bit vitamin B12 deficiency. So I showed how the expression of genetics can change during pregnancy. So how does that apply to sex? Everyone likes to talk about sex, right? So it's not as simple as XX and XY, but I'm not going to get into all of that. Basically, the important gene on the Y chromosome that produces males is the SRY gene. So what I think is that if you methylated the SRY gene, then that would turn off male development, and it would just default to female. And there actually are studies that say that SRY is methylation controlled, which is basically why which is basically why your gonads for males are where they are, and you don't have it on your face.
You could have something like that on the house.
So basically, I think how Luca's genetics works is that he/she was originally supposed to be an XX male, which is called de la Chapelle syndrome. And how that happens is that during the sperm formation in the father, the X and the Y accidentally cross over, and you get some of the Y on the X chromosome, and then the X chromosome with the SRY gene goes on to fertilize an egg, which results in an XX male, because even though it's XX, it has the SRY gene, which is enough to promote male development. And also, some XX male individuals have been reported to have a more feminine appearance, but under the belt, male genitals. So, in conclusion, it's the same the same diagram, but showing what's happening behind the scenes. So, Luca was conceived as an XXSRY male, and without intervention, the SRY gene goes on to promote male development, and Luca is born as a male. But with the message sent to the past through the pager, the mother eats the leafy vegetables, which methylates the SRY gene, producing a normal, healthy girl that is probably fertile, as some people may know if you've already played Steins Gate spoilers. So that's all I have for that presentation. If anyone